All right. Hello, everyone. Welcome back. Math 154, Week 7, Lecture 2, 7 weeks down of this summer session after today. Crazy how time flies. So, just going to take a couple minutes to go over our whiteboard, most of which you already know, hopefully, assuming you're watching all our lectures like you're supposed to. So, big old slab of my math lab homework, couple due today, couple due on Tuesday, couple due on Thursday, a week from today, because we will finish those sections today. So 4.3, 4.4 today, 5.1, 5.2 due on Tuesday the 13th, then 5.3 and 5.4 we will knock out today, so they will be due on the 15th, a week from today, 11:59 p.m. per usual. Your next Excel homework on the docket is 5.1 lines. That's going to be due on the 15th. I would like to remind you, this is a super friendly hint, wink, nudge reminder that your guided activities have little previews of these Excel files. It's something I've said many times, but I haven't said it in a few weeks. So just reminding us, because especially with this one, I find that a lot of people, when they do the charts, the graphs, whatever you want to call them, for this particular homework, they always end up with an extra line. You're supposed to plot a bunch of lines, graph a bunch of lines, like 5 or 6 or 7, something like that. And from what's expected versus what a lot of students actually end up doing is, again, a lot of students end up having an extra line. So what you can do before you submit for grading is you can take a peek at the guided activity 5.1 preview. You will actually see a picture of what the final chart, the final graph, again, whatever you want to call it, should look like. So if you count 5 lines on theirs, and it's not 5, I'm just giving an example, and yours has 6, something has gone wrong. If you see a particular pattern in the one in the workbook and yours doesn't exactly fit that pattern, then something went wrong. Maybe you have something else in there. Maybe you highlighted too much. Maybe you didn't follow the instructions list of the instructions tab precisely. Excuse me. All right. After that, we're only going to have either 1 or 2 more Excel files, but they will be coming at you quickly. I might even have to assign the last one before we technically get to the last chapter. But the good thing is it won't be an issue because really the stuff you do in that very last one that I would assign is, essentially the same stuff as things we were doing back in chapters 1 and chapters 2. In terms of quizzes, we're going to have a few more video quizzes. So the last few quizzes I'm going to throw at you are going to be in the style of that video quiz. We've only done one, and it was several weeks ago, probably like week 4, if I had to guess. So if you remember what that was like, you go to Canvas, you'll see 2 spots. You'll see a download link and you'll see an upload link. So you'll go to one link to download, and this is 5 questions, and this is based on chapter 2, so just kind of bringing up some old stuff since we're getting near the end of the semester. It's nice to rework in some old material every now and then. So 5 questions, and then you'll go to the videos in my math lab. So nothing that I created. These were the author created videos. I even remind you of how to get there in the instructions, even though I've reminded you many times, and you had a quiz question on it from video quiz 1. Although not everyone answered that correctly. Some of you answered to go to Canvas and to check my videos, but that's not what I meant. So you'll have a week for that. And again, spoilers, the next 2 or 3 of these quizzes will be in the same format. So 4 to 5 questions, a link to download and a link to upload. I will have to personally grade them, so you won't get feedback immediately. I won't grade any of these until after that deadline. And then the biggest reminder, the midterm dates, the 12th and the 13th, that's Monday and Tuesday coming up. Those are the only 2 days you will be allowed to take the midterm. If you email me on the 14th or the 15th and say, hey, Mr. Beckner, I forgot, that's too bad. You will just have a missing grade. If you have some kind of documentation for some crazy circumstance, then that's fine. Then we can work with that. But you would need documentation to have missed a test. Remember, this is a no notes, no books test, with the exception of that single page formula sheet, which only has 2 formulas that you find in Canvas. You are allowed to use calculators. You're not supposed to use a cell phone. You are supposed to use an actual calculator, whether it's your computer's or a handheld one. I do not care, as long as it uses your own work. You are required to show your work. You must number your problems. They don't have to be in order, but they must be numbered. Put your name on your work, and then you have to submit it in Canvas within 15 minutes. I am actually not going to make that link available until the 2 days of the midterm as well, just so I don't have a lot of students accidentally submitting video quiz 2 into the midterm spot. I'm sure someone will still do it. Historically, it always happens. Something gets submitted in the wrong spot, but Canvas is kind of a jerk to me, and not just me, all teachers, in that if you submit something wrong and I only give one submission, there's nothing else that can be done. That's it. So please make sure that you do not make a mistake. Please make sure that you pay attention. Again, if you submit the wrong thing, I can't clear that. I cannot delete your work. I cannot give you another attempt without giving the whole class another attempt, and that's just not going to happen. One attempt on the midterm, 20 questions, 2 hours. If you have any kind of accommodations, email me, remind me. I will make sure you get those accommodations for your midterm. Review in Canvas. So the review is available. The formula sheet's available. It's just where you submit your work for the midterm is unavailable. Again, you will see that live on the 12th and 13th. And I think that's all I really need to say, besides after you take your midterm, you show your work, you upload your work within 15 minutes. If you think you deserve any partial credit, you shoot me an email. Remember to say what day and time you're in for QR, because I'm teaching more than one of these. And then I'll get back to you within 24, 48 business hours. And I'll say, hey, yep, I got you your credit for questions 2, 3, and 7 like you asked for. Or, well, I got you 2 and 7, but number 3, you weren't quite there, so I couldn't do anything. And yeah, don't be terrified of the midterm, please, please, please. The review will let you know what to study. The midterm's going to flow a lot more like the homeworks versus the guided activities. It'll be much more simple concepts, again, like the homeworks. And just do your best, because that's all I can ask of you. But please study, 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 and put in the time. If you study for 1 hour, that's not doing your best. Study for 5 hours, study for 10 hours, study for 20 hours, whatever it is that you have to do. You should have already been studying, essentially, by doing your homeworks, quizzes, Excel files leading up to this. All right, sorry if you can hear my my dog shaking my table right now. He's under me. Anyways, that distraction aside, let's go ahead and pick up where we left off. We're going to be getting into another guided activity. And then, like I said, we're going to continue our work with 5.3 and 5.4. Per usual, if you have any questions, I'll be in the chat ready to answer them.
It's the intercept one, and it's page 204. That's too far. Here we go. All right, so for this activity, in the previous one we had figured out what the slopes of those were, and then we started talking about using that cookie cutter phrase, like the output is changing by this value, which was the slope, and then you go y units per x unit. That's what I mean. Now we're just going to talk about the intercepts. It's going to be a much easier way of saying things. It's going to be a much easier problem to tackle. So we'll go through these pretty quickly. So they're asked to interpret the y-intercepts. And let me do, so I don't have to keep going back and forth on that. Sometimes it's worth it to stay on that screen. Sometimes it's better to do things like this. What? Where'd it go? Technology, man. Okay. So this worksheet asks you to interpret the y-intercept. So we've said the y-intercept is often interpreted as a starting value or a fixed value. Starting, another word of that, is initial value. There's a lot of different ways to say the same thing in the real world, of course. So let's go ahead and get it. We have our 5-cent plan where we were paying 5 cents per minute, but then we also had that $20 fixed cost for fees, taxes, whatever. So we said the equation that we developed was y equals 0.05x plus 20, where x would be the number of minutes and y would be a cost in dollars. We used C and M when we actually wrote the equation, but I did say that we could use y and x as long as we wrote somewhere what y and x are. Now, when you have axes set up, this actually is declaring what the x and the y is by just writing y equals 0.05x plus 20 and then seeing minutes on the axis, the x-axis, and dollars to the y-axis. That implies that that's a cost and a number of minutes. All right, so just the y-intercept, which is the starting value, also the constant, the fixed value, so that's the 20. So if we're in 1a, the y-intercept is the 20, which is a cost. So the cost is $20 when 0 minutes are used. This is an initial fee. Guess I could have typed that. Oh well. So this 20, that's the fixed or initial amount. It just depends on context. Here, I could call it either. It doesn't really matter. I think most of us would call it a fixed fee, but you can also call it an initial fee because it relates to 0 minutes being talked. And then, like we said, we can always see that value on the Y-intercept. Now, we've talked about how in real world models, these don't always have to make sense, and maybe we'll get to that today. All right, second one, concentration of pollutants. And I don't know why they say there's an A and a B or anything like that. It's just A for all of these. So I guess I can just go number 2. For the concentration of pollutants, so we said there was an initial spill, and then over time, over some days, that spill gets weaker and weaker because it's diffusing, dispersing, whatever D word you want to use. And that rate of diffusion or dispersion was 0.8 parts per million per day. And that was the loss because it's a negative. But we're not asked to interpret the slope here. We're asked to interpret the initial value, which is the Y-intercept, which is 100. So that says that the pollution is 100 parts per million on day 0. In other words, this is the initial spill. For number 3, our Houston population. And I want to point out something on this one. They give you 2 different versions of this. The top one is what you would see. I thought I hit annotate. This is what you would see in Excel. And the bottom one, this is what it would actually be. So we talked long ago about how Excel sometimes will display a number that's rounded, but it actually holds the actual number in the equation or in the formula or whatever it is it's using in the cell. So it'll display this, which makes you think that it's really just 5 million. But the actual number that is stored inside of Excel is this 4.715407 million. So when it does any calculation, and when you throw in any year since 2005, 10, 22, 39, whatever, it is going to plug it into the bottom one. But again, when we visually see the equation, it's only going to show you this one. Now we can double click the cell, and up in the formula bar, we'd probably see that 4,700 if this was in a cell. Unfortunately, this isn't in a cell, it's in a chart, so that might make it a little more difficult to see. But don't really worry about that because we're generally not going to be dealing with these big giant numbers in our homework problems. So interpret, and they say please interpret both. I'm not going to interpret the top one because it's honestly pointless. It's just you're using a rounded number of 5 million instead of the actual number of 4.7 blah 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 million. So the, oh yeah, clear screen, go off of that. All right, so the population of Houston, well, that's the fixed or initial amount, is the 4,715,407 people. At year what? At year 0? Because we always say it's at the 0 amount, so you might go at year 0, and that would be wrong. Because this model is not using years as the independent variable as the x. You might go, yes it is, it says years right there. But it's not just using years, it's using something more specific, years since 2000. So if we said that the Houston population was 4.7 blah 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 million at year 0, that's not going to make any sense for several reasons. First of all, Houston wasn't around until at least 1776, and I think no one's going to have a problem agreeing with that. I don't know the actual the year Houston started, so please don't quiz me on my history. And that's not the point of this, but it's clearly, you know, somewhere in the 1800s, because that's when Texas was established. We weren't really heading west until sometime in the early 1800s, right? All right, so we can't say it's at year 0, but that's because this is years since 2000, so that's really at the year 2000. This is a very, very common way of doing a population model. That way we can make it a simple model like a line instead of a more complicated model like an exponential, like we'll see in chapter 6, or even worse, like a logistical model, which I'll never even show you in this course because it's out of our pay grade. So you have to be careful when you're dealing with models with years since 2000. If this was not a model that had years since 2000, if it just said years, I can tell you there's going to be problems with this if you trace it back to year 0. All right, so number 4, last one, that monthly interest. Now, we talked about how this is scientific notation. If that was a plus 11, that means the decimal will go right 11 times. But since it's a minus, the way scientific notation is, it goes left 11 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a whole lot of zeros, 10 of them to be specific. So that's 0.000000, that's 6, 7, 8, 9, 10, 2. That is the initial amount. Now this Y, this output is in dollars. So this is $1. I don't want to have to write that number again. So this is the interest on the initial amount on the bottom based on monthly balance. So that would be on $0 invested. Now here's the thing. We've said that interest on a very basic level, when we look at just one period, so a year, a month, a day, depending on how it's divided up, and we'll start getting into that more and more, it's just the product of the balance and the periodic rate. So if the balance is 0, 0 times anything is 0. But Excel, for some reason, instead of saying 0, they've given just this ridiculously tiny number. And that's because Excel makes microscopic boo-boos here and there, because it was trying to take a bunch of points and actually make this equation. And in that process, if we had maybe placed one of those points just a microfracture hair off, it would have caused that little rift, so to say. So this should really be $0. When I say this, I mean that number. Because how in the world is anyone going to get $0.00000000002? That's not even cents. That's not even hundreds of cents or thousands of cents. That's like billionths of a cent. No one's going to give you that. It doesn't exist. It's just 0. That's a situation where we have just a ridiculously small number. You just go ahead and call it 0 for the real world context, which makes sense because if you have $0 in a savings account, nobody's going to give you $0.0000002. They're going to give you nothing. Good day. And yes, that was a silly reference. Sorry. I can't help it sometimes. All right. So, something I wanted to point out, these graphs, we know how we make these graphs. You've had lots and lots of practice in Excel with this at this point, so I'm not going to remind us how to do those graphs. You would just have a table in Excel, you highlight them, and then you do insert the suggested chart if they give you one that's suggested, or you can just go to the pre-made layouts and pick one from there. Again, if any of this is not striking a memory, go back to the first week and a half of class videos and rewatch those, please. But how do we get these equations? Because that's going to be extremely helpful to know, maybe for homework, maybe for just working with things in class. And here we go. How to add a trend line and the equation and R squared. R squared is going to become later. I'm not going to talk about what it means yet. But this R squared value, we're going to talk about in chapter 8, which is not that far off. Chapter 6, we're going to be able to knock out in 1 week. And then chapter 8, we'll actually be able to knock out in 1 day if all goes as planned. Chapter 8 is really short. It's only 2 sections. Chapter 6 is 2 sections. Chapter 8 is 2 very short sections, in fact. So You highlight your data and your labels, you insert your scatter plot. I mean, that's literally what I was just talking about for making the graph. And scatter plot is what will make it look like dots. Then you go to add chart element and trend line, then linear. Linear makes a line. If you go to add chart element and then trend line, you'll see other options, and you don't have to make a line, but that's what we're going to be doing for now. And then add chart element, trend line, more options to display the equation and the R squared. So where are you? I'm not seeing it. You know what? I don't want to have to go on a wild goose chase. I'll just make one up on the fly. So let's just go X, Y. I'm not doing any context. We're just going to go numbers. And let's say if X is 0, Y is 2. And then if X is 1, Y is going to be 7. If X is 2, Y is going to be 12. I'm making a pattern here. Just trust me that it's right. And then 17, and then 4, and then 22. Now, when we're talking about real world values, they don't have to be exact fits of a pattern. When we talk about modeling things that have actually happened, it doesn't always have to see that constant slope. Every time I'm going up 1 in the X's, I'm going up 5 in the Y's. They don't have to be that. This 12 could be a 13, this 17 could be a 16, this 22 could be a 5 million if it really just didn't fit the pattern. Again, in a real world context. So let's see if we can follow what all this says. Let me do this, and then that was not what I meant to do. How many times do you hear me say that a semester? This is a joke, but I could make like an extra credit problem out of that. Someone go back, count all the videos. All right, so highlight the data and the labels. So I just called them X and Y, apples and oranges, whatever. Insert scatter plot, insert. And then let me just maximize this for a second so I can see it a little clearer. All right, which one's the scatter plot? Which one's the scatter plot? It's the one that looks like dots. I pointed that out over there. So insert scatter plot. It's generally the top left one. You don't want to do any of this weird stuff. And you might say, well, why wouldn't you want the one that's already connected? Because this is going to connect them perfectly, and models don't always connect perfectly, as we'll start noticing. All right, so there we go. We've got our chart, and we're just going to squeeze that over there. Then we say to put in the line, you go to add chart element, trend line, linear. Make sure you're taking these notes down. So add chart element, trend line, and then there's a few options, and I'll even show you how they look. So look at the graph as I'm doing this, and I'm sorry that I'm covering up part of it, but I can't help that. Linear forecast is the same as linear, except it kind of extends it out further. There's no reason that we ever use that in this class. Moving average, this is really useful for modeling population dynamics, maybe like how many people have had a virus. So they'll measure it every single day, but the measuring is consistent. Maybe there's no measuring on weekends. So looking at the day-to-day chart isn't exactly a great model. So people will just say, all right, I'm going to, at each point, I'm going to average the 5 days prior and the 5 days ahead, something like that. It doesn't have to be 5. That number is chosen by whoever's doing it. And then it gives you a moving average. And you can see this one doesn't even look like it makes sense. So let's not do that. Let's go with linear. Boom. Now, again, because this is a perfect model, these fit perfectly. They do not have to. Then to actually see the equation, we go to add chart element, trend line, and more options. So add chart element, trend line, more options. And then a menu pops up over on the right. And then you'll see down here, you can display the equation and display the R squared. Now, again, this R squared, we're not really going to do this until chapter 8, but I like going ahead and pointing it out while it's relevant. So display the equation. Now, this menu is covering it up, but it did pop up right there, and I don't want to close this yet. Let me maximize it. Okay, perfect. So there's the equation. And then if I display the R squared, what this is a value of is it shows you how well the data fits. And admittedly, I'll go ahead and tell you 1 is a perfect fit. So if this data did not fit perfectly, it would look quite different for that R squared. I'm going to copy paste this. Copy, paste. I'm going to make another one of these, but I'm going to make the Y values not fit this perfect as X goes up 1, Y goes up 5. Let's make this a 6. Let's make this a 13. Let's make this a 19. and then let's keep that at 22. So I'm going to highlight, insert, scatter chart, pick the top left one. See, this doesn't look like a perfect line. It's kind of close. You could probably, do a nice spitball guess there, and it would hit some or most of them, and we'll start talking about that later. But for now, all right, so we got our chart. Make sure you click the chart so that you get the add chart element. And then we're going to add the trend line, linear, and look, see, that one's not a perfect fit. See, this is the first one. This is the second one. When I click the chart, it shows you which data is being highlighted. See, that's not a perfect fit because this was not a perfect model. And now when I go to insert the extra stuff, the equation and the R squared, you can see that the equation has some decimals in it now because, well, first of all, it wasn't that as x goes up 1, y goes up 5, it was never consistent. So they're just making a kind of a best guess. Excel does lots of crazy math to get that equation. Please don't worry about how we get that. It's insane for us. It would take me a month to teach it and to get you to be able to do it perfectly. And it's extremely time consuming. This is why you go, thank you, Excel. I love you, Excel. And then the R squared, 0.9849. That's pretty good, but it ain't perfect. Again, 1 is perfect, as we'll discuss in chapter 8. So just kind of foreshadowing some things there. All right. Cool. .3, I don't really have a lot that I have to go over in this because I've already gone over almost every single one of these aspects with you. So this is not going to be seen very long. I'll put a couple of graphs up here as reminders, but again, this is nothing new. I have already talked about all this. I don't really know why 5.3 is a section besides the guided activities, but it is what it is. And I'll talk about that in a minute, but the Y-intercept of a proportional relationship is 0 and generally not written. So that's when your line goes through the origin, and it doesn't have to go up. It could go down instead. This is proportional, which means your equation just ends up being y equals mx. It's just a number times x. You only have just the variable amount. There is no fixed or initial amount because it's a 0 and nobody is going to write plus 0. On the contrary, when it's not going through the origin, that means it's not a proportional relationship. It means there is a non-zero initial amount. So this is not proportional. And it has the full mx plus b, the mx being the variable amount and the b being the fixed amount. And again, for this first one, the y-intercept is 0. Y-intercept, excuse me, I forgot to write intercept. For this one, it's b. So this height right here is b. So remember your slope-intercept form is y equals mx plus b. That mx is the variable amount, the b is the fixed or initial amount. And we've already talked about how if you know any slope and any coordinate, you can plug these 3 numbers in to find b. Again, we did an example like that last class. Not going to do it again. Like I said, most of this is just retreading. A couple new words, though, coming up. The larger the value of m, the steeper the line. So again, that's something we already talked about. If we have a line that looks like maybe this, let's say this slope is +1. I'm going to specifically write the positive. You normally don't, but I'm just being meticulous. Then maybe this steeper line would have a slope of, say, +3. Or maybe your line is pointing down. This might be a slope of -1. I'm not caring about the intercepts here. But then this steeper line might have a slope of -2 or -3 or -4. I'm just going to go with 3. Again, nothing new there. Retreading. This is new for the chapter. This is nothing new in terms of techniques you should be able to handle, but this is new for the chapter. If you're given an equation that's not in this y equals mx plus b form, that's what I mean by in this form. By this form, I mean this form. where it's solved for y. If you have an equation that's not solved for y, it's probably a good idea to solve it for y because that's what enables us to graph it much, much easier. Yes, you can graph lines that are not solved for y. Yes, if this was an algebra class, I would teach you how to do that. This is a quantitative reasoning course though, so we like to keep things in common forms and that way it's as simple as possible. So just solve it for y if you get one. So for example, if you had 2x plus 5y equals 10. So here's your mathematical model, but it's not in an dependent, independent kind of situation. It's not just saying y is this thing based off of this other thing. It doesn't say apples equals blah, blah, blah in terms of oranges. It says if you took 2 times the number of apples plus 5 times the number of oranges, you should get 10. Doesn't have to be apples and oranges. You get my point. So we just solve it for y. I like to put a little dotted circle around the thing I want to solve for. Now this 2x, you're just pretending like it's a constant. You're going to move it over like it was just a 2. But it's not a 2. I don't want to put it under the 10 because those aren't like terms. I want to kind of stuff it to the side so that these 2x's cancel and you get 5y equals, and then that's 10 minus 2x. Now again, I like to remind myself what I'm solving for. Now I want you to pretend that this other side is just 10. If this was 5y equals 10, you would divide both sides by 5. That's exactly what you would do. Everyone should understand that. But the right side is not just 10, it's 10 minus 2x. Do you know how much effect that has on what you do algebraically? None. You do the exact same thing, except you want to do it like this. You want to divide every single term by 5. See, doing this, I'm going to change colors just because I don't want to have to do that again. This is the same thing. It's the same exact thing as this. Dividing the entire right side by 5 is the same as splitting up the division. But if you do it this way, you're probably likely to want to say, oh, this 10 and this 5 reduce to a 2 and a 1, and that's wrong. They don't reduce to a 2 and a 1 in that form. You cannot do that, you cannot do that, you cannot do that. But when they're split like this, you can. These 5s will cancel. This 10 and this 5 do make a 2, and then you leave that piece with the x alone, and you get y equals 2 minus 2x over 5. Or if you want this to look more proper to have the x term first, that's y equals negative 2x over 5 plus 2. These are the same thing. They are just written in a different order of terms. And you might be thinking, well, Mr. Beckner, why isn't this positive and this negative? Why did you move the location of the minus? Because the minus goes with the x term, so the minus has to stay with the x term. This 2 was positive, so that needs to be a plus. So in this form, you can see that the m is negative 2 over 5, and the b is 2, which means this is your variable rate, and this is your initial or fixed amount. You can't see any of that in 2x plus 5y equals 10. You can't tell me the rate at which this thing is changing. You can't tell me what it started at. It's no good. It's not helpful for us to interpret it as a quantitative reasoning student. Again, sure, you can graph 2x plus 5y equals 10 in ways without doing anything to it. But we're all about the interpretation. We're all about seeing that, okay, every time x increases 1, the y is decreasing by 2/5. Or you can say that the slope is you're going to go right 5 and down 2. And we can see that we initially have 2 of whatever this thing is we're talking about. That's where this is helpful. All right. And then just a couple last minute words. Again, everything after what I have highlighted here, nothing is new. We've already talked about that. Accumulation just means you have a positive slope. Depreciation means you have a negative slope. Those are just 2 words you might see in the real world or in a QR class. Okay, so this thing is accumulating at this rate. That says it's going up. Or this thing is depreciating at this rate. That means it's going down. So if you're talking about your home in the long term, your home will accumulate value as long as you're maintaining it. If you're talking about your car over a long period of time, your car is going to depreciate in value because car values go down and home values go up on average in the long. Now, yes, if you have got some 1968 Shelby GT 500 with a 428 under the hood, blah, 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 car stuff. Sorry, I love old muscle cars. That car is going to appreciate in value because it's rare, it's highly sought after, it's cool, whatever. So yeah, there are cars that do appreciate in value, but if you've got a 2005 Honda Civic running around, trust me, it ain't going up in value tomorrow or a year from now or 5 years from now. Now, it's a Honda Civic, so it's not going to depreciate nearly as much as, say, a Volkswagen Jetta. Yes, I am going to fire some shots at them. All right, enough fun. Again, this part, the sloping, rise and run, we've already talked about that. Not going to talk about it again. Just a reminder. And that closes out 5.3 in the notes, arguably. That's all the notes for 5.3. However, dramatic pause. We do have more of these guided activities I want us to do. And it is not that one. I'm on the next page, sorry. Here we go. Oh, I don't know why I said that. We never even started the guided activities for 5.3. My bad. So we're done with the notes. We got guided activities. But the point of what I was trying to say there, sorry about that, is these guided activities say 5.3, still 5.3, still 5.3. These guided activities say 5.4, and you'll notice it says statistics. And if you remember, I've said we don't cover anything with statistics. However, whenever they modified this workbook, so we got a new version in 2019, they put stuff that was in 5.3 and 5.4 in the guided activities that doesn't need to be in 5.4. So we are going to talk about some of this stuff, most of this stuff, in fact. However, we're not going to be doing any statistics. This stuff that you're seeing right here should still be part of 5.3 in my opinion. So we will still do this guided activity. That's the only time the entire semester that happens. And that's just because, in my opinion, the textbook company made a mistake in organization. All right, so let's leave that for now. Let's get back to the start of 5.3. This stuff, they're just talking about how equations can be written with C and M, letters that are much more tactile for the problem. And these were all things that we saw before. But they could also be just used in Y and X, as long as somewhere on your own you're writing what X is and what Y is. So this 1 is the same as this 1. This 2 is the same as this 2. This 3 is the same as this 3. And you might say, well, hold on. Number 2, they swapped the order. Well, we just talked about that in that very last example we just did, that 100 minus 0.8x is the same thing as negative 0.8x plus 100. Oh, Mr. Beckner, this is 0.5%, this is 0.005. Well, 0.5% converted to a decimal is that. Please don't ever write equations that aren't in Excel this way. Please don't ever do that. If you're writing an equation that's not in Excel, make that 0.005 and then your B for balance. This is just silly. Okay. Small numbers, fuzzy numbers. The following table shows Palm Coast, Florida as the fastest growing metropolitan area from 2000 to 2010. Fastest growing, meaning that their population is growing the fastest. I didn't say anything different there, did I? No, but that was intentional. It means that if you look at the change from 2000 to 2010, that it would be the greatest. Now, does it have to be the total change or the percent change? Well, let's just see where we are and if we can figure out which that is. So most populous, so these are the highest population places. So we got New York, which went from 18.3 million to 18.8 or 9 million, depending on how you want to round, which was an increase of about 574,000, which was an increase of 3.1%. So this is just total change and percent change. That's what both of these are. These are total change, which is new minus old, and then this is percent change, which takes the total change, this 574, and divides it by the original of the 18.3 million. So that's how both of those columns are accounted for. The difference of new and old, and then the fraction of the change to the old converted to a percent then. So if you look in this table, the biggest difference you see is 1.23, and that's for Houston, Sugarland, Baytown. I don't know if that's a T or an L. I can't read that. It's too fuzzy. They need some 720p charts in this thing. So that's got the biggest total change, but they said Palm Coast, Florida is the fastest growing. So I guess we're not basing this off of total change. Maybe we're basing this off of the percent change. So let's see, percent change. 92%, that's the largest one out of all those. And look, it's Palm Coast, Florida. So when they talk about fastest growing, they're talking about relative to the size. Because Palm Coast, Florida only increased by 45,000, whereas New York increased by 574,000, and Houston increased by 1.2 million. So those were bigger changes, but when we consider relative to what's already there, relative to the original size, this is the fastest one. Because look, this was about 50,000, this is about 100,000. It almost doubled in 10 years. New York did not almost double in 10 years. It didn't even come close. It barely added on to the population. So that's because New York is already pretty well established, whereas this Palm Coast, Florida town is pretty new, and you've got good construction crews in there, good politicians, low tax rates maybe for local regions, things like that that are just kind of initiating growth. And maybe in the next 10 years, maybe right now, maybe this population is 150,000, maybe it's 200,000. I don't know. I'm not going to pull up the data. All right, so what's the point of this problem? We got lots and lots of different areas, cities, whatever you want to call them, because some of these are like, you know, several cities lumped together, just metropolitan areas, kind of like Hampton Roads is a metropolitan area composed of Suffolk, Portsmouth, Chesapeake, Virginia Beach, Norfolk, Hampton, Newport News, and yeah, that's it. I said them all. So use the values in the table to determine the linear equation of the form y equals mx plus b between the 2 points for Palm Coast, Florida, where x is years and y is population. So they're telling us they want our independent variable x to be the number of years, not years since 2000, just years, and then y will be our population. Okay, so we're using these two numbers, the 49,000 and the 95,000. So how do we come up with the m and the x and the b? Well, y and x are going to be just numbers. I'm sorry, what did I just say? Y and x are numbers? No, y and x are going to be the variables in the final equation. It's going to be something like y equals 3x plus 5. That's what we're after. But to calculate the m, we need to know the slope. The slope is the rate of change. It's the change in the y values, which is the population, over the change in the x values, which is the years. So our slope will be the change in pop, new minus old, over the change in years, new minus old. So for this problem, our m should be the change in population, which is 95696, minus the old 49832, then over, and the change in the years, we went from 2000. I hope my pen is showing this because I've got a menu right here that I can't see it. This should say 2010, and this should say 2000. I think I'm in the right spots. So we do 2010 minus 2000. If you do that subtraction, you're going to get 45,864 divided by 2010 minus 2000 is 10. If you do that division, you're going to get 4,586.4. That is our slope. This is the rate of change in the population per year. That's what the slope is representing here, because we're talking about change in population versus change in years. So that's going to be part of question 2 that I will have to scroll down and erase everything to get to, so let's hold off on that. But that's our M. For our B, we just talked about a second ago, we didn't do an example, but we did one last time, how as long as you have a point and a slope, you can plug those in to find the B. So remember, we're going for y equals mx plus b. So we're going to plug a number in for the y, we're going to plug a number in for the m, which we just found, and we're going to plug a number in for the x, and then we're going to be able to algebraically solve for b. Well, what y and x do you plug in? you could plug in the 49,000 with the 2,000. I can't actually circle that, unfortunately, because menus. Or you could plug in, so pretend like there's a red circle around 2,000. Or you could plug in the 95,000 with the 2010. So pretend there's a blue circle with the 2010. It doesn't matter which points you use. It doesn't matter which points you use. At the end of the day, you'll get the exact same answer. Now, if any of these have a 0 in them, that's the one I would use because zeros are easy to plug in, but we don't have that here. I think 2000 is easier to plug in than 2010, so that's what I'm going to do. Let's go back to red. Okay, so I'm going to plug in the 2010 numbers. I know this is in red, so just please ignore that that's red. I'm using these numbers. So that's the Y value. 95,696 equals the M, which we just found to be 4586.4, times the X value, which is the 2010. What am I doing? I said I was going to use 2000, but I circled 2010. Let's just go with it. I already said it doesn't matter. I made myself a liar. I said I was going to use the 2000 numbers. We're going with 2010. So that's times the X value, which was 2010. And then plus, we're not plugging a number in for B, so we leave it alone. Again, at the end of the day, when I solve for B, if I had plugged in the 49,000 and the 2,000 into here and here respectively, here, you would end up with the same B. All right, I am going to have a difficult time putting the calculator on the screen at the same time, so you're just going to have to trust me that these numbers are right. 4586.4 times 2010, please try this on your own, is going to be 92, why does that look wrong? 664, let me double check that, 4586.4 times 2010. I'm just not used to plugging in those numbers. I usually do the 2000, that's why. So that's 95696 equals, this number is 9218664 plus B. Then to solve that, all you do is you subtract the 9 million number on both sides. So the minus 9218664, just doing very basic algebra here, which tells us that, and if you do that subtraction, you're going to get 95696, 95696. You're going to get negative 9,122,968 is equal to B. So we have our M, we have our B. We're going to plug those numbers in to the M and the B to get our model. So our final answer, the equation, the model, is Y equals. The M was the 4586.4. Sorry if you hear that siren. They heard I was doing math, so they're coming to get me. 4586.4. X, that's the M and the X. This was the slope. We found the slope by doing 2 points and finding their changes, their rate is a change. Then, because the B is negative, I'm actually going to write a minus here, and there's the 9,122,968. If you really want a comma here as well, you can do that. This is the answer. That is the equation of the model. This is a very common way to find an approximation to modeling some population over a short period of time. This is not a great model, but it would have been if we had done it a slightly different way that we'll do later. Interpret the slope in the Y-intercept. So unfortunately, I'm going to have to clear my screen. So when I clear my screen, I'll scroll down and I'll just write that stuff again because I've got it. I've got the numbers in front of me now. So clear, scroll, go back to annotate, interpret the slope and the Y-intercept. All right, so the slope is slope of 4586.4. I just want to write that down so you see it again. It means that the population is increasing because it's positive. 4,586.4 people per year. Now you might be saying, why didn't you just say 4586? Because we're dealing with a large population. If we were only dealing with a dozen or 100 people, I would round that to the nearest whole. But when we talk about very, very, very large values with people, we keep the decimal. So that's the slope. The y-intercept, or the initial value of minus 9,122,968, that the population at, now remember, y-intercept means the initial amount, which means the zero. So at year zero was negative 9,122,968 people. What? Huh? At year zero, there were negative 9 million people in Palm Coast, Florida? Guess what? That doesn't make sense. I said last class that y-intercepts, when we're dealing with real models, do not always have to make sense. And I even alluded to the fact that we're going to deal with these two versions of population dynamics, one where we just use regular years, so year zero was 2,020 years ago. And sometimes we'll use a year since, like that year since 2000, where year zero in that sense would actually be the year 2000. Year zero in the model, in the real world, relates to the year 2000 then. And it doesn't have to be year since 2000. I can make a model where it's the year since 2005, the year since 1984, the year since 2020. So this does not make sense because population or linear population models awful for very long periods of time. On top of that, Palm Coast, Florida didn't even exist. It would not make sense to model a population any year before it actually existed. That's like going into negative years for that region. So also, this town didn't exist in the year zero. Can't model that way. How are we on time? Okay. Number 3, let me go back and write the equation from number 1. It was y equals 4586.4x, which was the slope, and then minus the 9,122,968, which was the initial amount of people, which we said didn't make sense for various reasons. Can't have negative people. Can't model a population when it didn't exist. Don't want to do linear models for these ridiculously long amounts of time. So number 3, use the values in the table to determine the line between 2 points of Palm Coast, Florida, where x is the number of years. And this is not correct. This is a typo in the textbook that I wish they would fix, at least in the electronic version. X is supposed to be the years since 2000 now. That's a major difference. They've really screwed up that problem by missing that detail. It's not just years, it's years since. If they said x equals years, then number 3 would be the exact same problem as number 1. Not the point of this. So now we want to take this to a shorter time frame for modeling the population, which I've already alluded to is generally better for lines. You don't want to do a population model for more than like 30 or 40, 50 years with lines. It's a terrible idea. All right, so we're going to use the exact same 2 points, which I'll just write them up here. But now we're doing years since 2000. So what you're going to notice is that the year 2000, which was originally in that table, is now going to be a 0. The year 2000, when we're using x being the number of years since 2000, is 0. And the population then was that 49,832. And then the other point was the year 2010, which would be 10 years since 2000. Oh boy, that was not what I meant to do. Okay, that worked somehow. And then this population was the 90,000 something, 95696. I don't really want this comma here. That looks awful because of the comma for the point, and you can see why I just deleted that comma. So I just wrote these as coordinate pairs. They're literally the same thing from the table, but now the year 2000, we've turned into 0 because our model is saying, hey, 0 is now just 20 years ago, currently speaking. And the same thing for this. We're going to do the exact same thing as in number 1. We're going to find the slope by doing the rates of change. We're doing the y's on the top, the x's on the bottom. We're doing new minus old. So we go 95696 minus 49832, literally the same subtraction. In the bottom, instead of doing 2010 minus 2000, because x is now representing the year since 2000, our x values are 0 and 10. So 10 minus 0. So the bottom looks different, but what's interesting is when you do the subtraction, you get the same value as last time. That's actually exactly what always happens when you change from a total years overall to a year since model. The change in years won't matter where your time reference starts, but something will change later, trust me. And the top is the same subtraction. That was the 45864, which doing the division ends up giving you exactly the same slope. This is a very important concept. No matter what type of model you use, a years or years since, the slope will come out to be the exact same. But spoiler alerts, the intercept will not. All right, so to find the y-intercept, I'm going to change colors just for make this a little prettier. We're doing that y equals mx plus b again. We're going to plug in any number for the x and the y that we like out of these two options. We can do the 0 and the 49,000 or the 10 and the 95,000. The m is the same m before. We're going to plug that in there, and we're going to find the b. Now, I'm going to use this point, definitely. I mentioned earlier, if any of them ever have a 0, which is pretty common in a year since model, that's going to be the easier one to plug in. So the x value is the 0, the y value is that 49,000. So we go 49,832 equals, the m was the 4586.4 times the x, which is 0, then plus the b. Again, this is the y value, this is the x value. I did not plug in the same y and x value as you saw me do in number 1. Again, I could still plug in the 10 and the 95,000 instead. You will get the exact same value of b, but your algebra will be more difficult. You'll have to do the same type of algebra as last time, whereas this time, since anything times 0 is 0, you just get 49,832 equals b instantaneously. So this is the initial amount. So our model is y equals 4586.4x, so there's the variable amount, plus 49832, there's your initial amount. Oops, let's try that again. Same slope, different y-intercept. 8, that looks like I wrote a wrong number. 49832. It looks like I wrote a wrong number because I did write a wrong number, to be honest. I wrote the 8 twice. You know what's awesome about this model? The interpretation of the initial value makes complete sense. This does not say at year 0 the population was 49,832. This says 0 years since 2000 the population was 49832. Which makes complete sense because look at this, it's exactly what we were told. So that y-intercept makes much, much, much more sense, and I'm about to write those interpretations. Let me do this. Question 4, if you flip to the next page, says interpret the slope in y-intercept. So question 4 is exactly the same as question 2. So what I'm going to do is I'm just going to erase the block for question 2 here. And I'm going to put 4 here instead. So now I'm just saying we're doing question 4. I'm not saying question 2 is disregarded. I'm just going to put the answer to number 4 here so I don't have to erase what's on the screen. I'm trying to help y'all out. All right, so Interpret the slope and intercept. I don't have to write the slope since you can already see it. So we're going to say that the population of Palm Coast, Florida, PCFL Palm Coast, Florida, was increasing by 4,586.4 people per year. We can't say per year. We got to say per year since 2000. And it makes more sense to say it that way. We don't want to say per year because then you might say, all right, so in 1500, we were increasing by 4,586 people a year. In the year 17, which was a long time ago, the population was increasing. It wouldn't make sense then. But if you're talking about 2001, 2002, 2009, 2030, this will be a lot closer to the actual value. Now, I'm not saying it's doing this exactly. I'm saying this is kind of like an average. Then the intercept, we can say that in the year 2000, the population, so the year 2000 is 0 years since 2000, the population was 49,832, which makes perfect sense. Your interpretations for population models tend to make more sense when you look at a shorter time frame, when you use a year since. When you're using years and going all the way back to the year 0, 20 years ago, it is much, much, much more difficult to model population dynamics. Even exponential equations aren't that great when you look at 2,000 years. Lines are awful because if you actually went through and looked, I don't want to erase anything. If here is 2000, the population was basically 0, 0, 0, 0, 0, 0, 0. I mean, maybe there was like 100 or 1,000 people there before America came over and did what it did. So, you know, hundreds of people, thousands of people, something like that. Just pretend like this is a little higher, I guess. But then all of a sudden, it just explodes for Palm Coast, Florida. So trying to use a line to approximate this is a pretty awful model. So if the black represents the actual people over time, the red would be a linear approximation to it, which is just trash. All right, so there we go.
Just had to set up the next video, and here we go with that one.
That guided activity from chapter 5, specifically, long dramatic pause so I can find it. All right, so I said that, big zoom, this says the following things go in 5.4. Okay, you could argue that they go in 5.4 because this is going to be Excel using something known as linear regression, something that we're not going to talk about at all, except for the fact that we let Excel do the job for us. But because we're not actually talking about the mechanics of it, we can still borrow these Excel charts. They were perfectly fine in 5.3 like they were in the original edition of this book. So we're not going to be doing any of the crazy statistics. We're just going to kind of talk about how it relates. So something that I have mentioned numerous times already, in the real world, quantities don't always vary in a perfect linear fashion, especially when we talk about financial dynamics, especially when we talk about anything having to do with people, pollutant concentration, as they kind of talk about, blah, 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 blah. So sometimes instead of saying we get an exact linear model, we just say it's a linear trend where the line can approximate some of these things, but it's not necessarily going to hit that nail on the head perfectly. So like here, if you look at 1985, this dot is perfectly on the line. This one's kind of far off. This one's kind of far off. And when I say kind of far off, that's subjective, of course. And then this one is exact again. Now, we went through a process where we actually made a line and we we are about to do that, never mind. So you might say, well, why not take a line and just anchor it from the first and the last points? That's actually a good method, and that's what we're going to do, the thing I thought we talked about, but that's because I've just done this so many times that sometimes I forget what I haven't done. All right. But just using a first and a last, that's not always a good approximation, especially when you want to go outside of these boundaries. Sometimes it may be a little better inside. Sometimes it may be a little worse inside. It just depends. So this right here, what you're looking at, this is what's known as a line of best fit. A line of best fit. So Excel uses this thing called linear regression. It's this mathematical process that it's the thing I mentioned probably last class that it would probably take me a month to teach it to you. It's extremely tedious, it is very time consuming, and we thank Excel for doing all of that work in the snap of a finger for us, because that's the beauty of computational mechanics. So this line is considering every single one of these points, and it's trying to, you could think about it as trying to minimize the average distance from the line to the point in a vertical sense. If that confuses you, don't overthink it. Just think that it's trying to make this line fit all of these points as best as possible in consideration of all of the points, not just the first and the last, which would be like an anchored method. So Excel somehow chooses this best fitting line, the line of best fit that I mentioned, and they say that we'll talk about it in chapter 8, although we actually won't. So Excel manages to come up with this equation, and I showed you how to get this equation last time. So if you don't remember how to put that in an Excel chart, then go back and watch last class's video. That's the beauty of these recordings. I don't have to always repeat myself. So we have our slope and our y-intercept. Now that y-intercept had an e, which meant it was times 10 to the 7th, which this is like a 4 with then 7 zeros after it, a very, very big number, or because it's negative, technically a very, very small number. So that's saying that the y-intercept is negative 40,000, which we're talking about millions of dollars. So remember, the y-intercept talks about back at 0, which since this is years, we're talking about year 0. And that makes no sense for several reasons. First of all, we're talking about Social Security outlays or expenses. So that means that at the year 0, we were spending negative $40 million on Social Security. Well, that's impossible because the least we can spend is, a penny or $0 more specifically. So how do we have spent negative $40 million? That doesn't make sense. Another way it doesn't make sense is, why would we even talk about Social Security in the year 0? America did not exist. Social Security definitely didn't exist until FDR's New Deal in the, don't quote me on this, 40s, roughly. Again, roughly. I'm not a history teacher, so please don't judge me there if I'm off by a decade. So it would not make sense for this model to even go further into the past than when this idea was started, because 1 year prior it was 0. The year prior to that it was 0. All those others it was year 0. So it's more like this model would be like, all right, 0, 0, 0, 0, 0, and then your New Deal starts, and all of a sudden your Social Security expenses pick up, and maybe they actually pick up in a model that looks more like this, which they did not do it that way. They used dots, so they're like 0, 0, 0, 0, 0, just for single years, and then all of a sudden the New Deal happens, and then we get our expenses and whatever that actually looks like if you looked at a longer span of time than from 1975 to the current year, or at least a few years in the past. All right, so that's our ultimate goal, is to kind of deal with that. But for now, what we're going to do is that anchored method I was kind of talking about. Instead of actually accounting for every single one of these points, all we're going to account for is the first one and the last one. We're going to make a line connecting them. We're going to find its slope. We're going to find its equation. And then ultimately, we're going to take that anchored model and we're going to compare it to the model you're looking at without the anchors, where all of them are being used. So that's what this says. Guided activity 1. The following table gives the amount of money spent on Social Security in this country in millions. So this is not 64,000 blah, blah, blah. This is 64,000 million, which would be really 64 billion. So this right here is not 944,000, it's 944,000 millions of dollars, which would really be 944 billion, and again, some change. Take the first and last data points, which they remind us are here. First, last, see 2020, we didn't have this data yet, that they only have up to 2017, so that's why it's blank, so we can't use 2020. 2017 is the last completed one, and we want to find this slope. All right, so I'm back to, I don't really think I'm going to be able to do this on another page, so you're just going to have to deal with me writing on this in my ugly handwriting version without that program helping me, as well as having to erase it quickly to move on. So our slope is y2 minus y1, that's the difference of the money values, then 944,878, and then millions, minus then that's 64658, all divided by the change in the x values, which is 2017 minus 1975. All right, and I am going to go maybe a little bit quicker today. So that top should be 880220, yes. And then the bottom, 2017 minus 1975. That's 42, right? Yes. And then I can't pull up my calculator right now, so you'll have to trust me that if you do this division, you're going to get, doing this manually, 20957.62. If you round it to 2 decimals, they say to 1 decimal though, so 20957.6. So that's 20,957.6 is our slope. So that's the number we can put in our equation if we were writing the equation here. So we'll hold on to that number, write that down because it's going to get erased. So write that down. Right, just like all your notes, you should be writing down. And then they say to interpret this as a rate. So that sentence, that cookie cutter sentence that we have done before. So we would say that Social Security outlays, that's the output, expenses. So outlays, expenses, same thing. Social Security expenses have been, well, the slope is positive, so I can be, instead of just saying changing, I can say has been increasing at a rate of, and then this is where we use the slope, 20,957.6, and that's in millions. So 20,095, I may have said that number wrong, but I've got it right here, 57.6, and then millions per year. Not per year since 2000. We never said that anywhere. It's just per year. We are considering the year 0 in this model, whether we should or not. Now, if you didn't want to write this in that goofy 20,000 millions, you could have said $20 billion instead, with all the other numbers in place, and that would have been okay. So again, that's our slope. Hold on to that. Don't delete it from your brain. Write it down, whatever you have to, because we're going to use it again. But I do have to clear my screen. All right, next they say, draw a line between the 2 points on the following graph. Now you might be thinking, 2 points? 2 points? I see lots of points. I see way more than 2 points here. They're talking about the 2 points that we used from the slope above. They're talking about the first and last. Again, I call this an anchored approach. We have the line of best fit, and then we have the anchored approach. This is not an official term. This is just what I call it, because it's like we're using the first and last to anchor, to tether a rope together. So we don't care about what happens in the middle. We're just drawing a line between them. Now, I'm going to do this wrong at first. Here's what I see a lot of my students do, and we actually get to work together. They just make all these bunch of little line segments, just drawing straight lines between each of these. And I know these are a little curvy, but I'm doing the best I can. Imagine those were all teeny little line segments, and it's wrong. They did not say draw a bunch of line segments. They said to draw the line from the first to the last point. So we're just trying to connect the first and the last. I'm going to try using something to make this a little better, but it's still going to be difficult. All right, so that's there. And this one, oh, that was a pretty good guess. I think I got it on my first try. Look at that. I will never do better than that quickly. You just witness history. I used a folder to kind of anchor my dots, but I placed it perfectly on the first try. And again, if I didn't, I was going to have to move it blindly until I got it right. So there's our line. And of course, I had to goof up the arrow just a little. Let's make that look a little prettier. There's our line. Just connects the first and the last. This is the anchored approach. So that's it. That's the entirety of problem 2. We can see that there are bigger gaps here, 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 and even here, versus that previous example. This is just me showing a gap, how far off the estimator, which is the line, is from the actual data, which is the points. Whereas before the line, let me just try and draw something that's pretty close. Before the line looks something like, it was a little below on the ends. Oh, I'm gonna nerf this. I'm gonna do my best. It was something like this. This was about what the line looked like before. That was the previous page. So we can see the red line's a little higher. The blue line's a lot closer to a lot of the dots. It even went through a couple of dots. I think I even nailed the specific years it goes through. I might be off by 1. Doesn't matter. Again, that was just a quick attempt. So they're not the same picture, they're not the same slope, they're not the same intercept. They make different approximations. You might think that that blue line is always better because, oh man, look how bad this one is in this section. It's so much further off than at the beginning and the end, especially in comparison to the previous one. However, while it may be better in this region, if you go 5, 10, 20 years in the future, maybe the red one's better. We don't know, and I'm not saying that this is always better. I'm saying it's kind of a flip of a coin. It's going to vary from problem to problem. All right, compute the equation of the line by plugging in a point from before and the slope that we found before. So before we knew that the slope was 20,957.6, and that was in millions. And the point that I'm going to use is the first one. You can certainly use the 2017 and whatever value that was, but I'm going to use the 1975, 64,658. That's the point I'm going to use with that slope. So that's our x and our y. This is the x value. This is the y value. This is our m. So we just plug those numbers in. So the y value, 64658, is equal to the m, which is 20,957.6, times the x value, which was 19. That's a 75. I know it kind of looks like a 9. And then plus the b. Again, I just plugged those 3 numbers into those 3 variables. We don't know the y-intercept. That's the whole point of what we're doing here. Again, just trust me on this calculation, and please try it out on your own as well. 20,957.6 times 1975 is going to be 413,64658 equals 413,912.60. Then we have our plus b. So that means we got to subtract that number on both sides. I'm just going to abbreviate it in the negative 413 dot 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 dot. It's a terrible looking one. 413 dot 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 minus 413 dot 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 dot. Just saving myself some space. And then if we subtract 64658 minus that 41391260. Hold on, I just typed it in my calculator. You get 413,266,02, 413,266,02. Okay, that's right. So that's our B, that's our Y-intercept. That's like our starting value, right? Question mark? I did something wrong intentionally just to see if everybody's on their toes. I have this as a positive value. But if you take 64,000 minus that number is really 41 million, this is definitely going to be a negative. So I was trying to keep you on your toes there. So that's a negative b value, which quite often negative b values don't make sense, especially when talking about money for an expense or population size or something like that. All right, so now that we have the m and we have the b, we're going to plug them in to the, to the m and the b in the standard equation, but we're going to keep the y and the x. We're not going to plug in that point anymore because we want to see what this thing is forever and ever and ever. So it's y equals 20,957.6x and then minus 413,26602, which is 41,326,602. Now again, that is actually in millions, so that 41 million is really 41 billion. I'm sorry, if it's in millions, we're adding on a whole set of 3 zeros. So trillion, that's representing 41 trillion in a negative aspect. Everything is in millions of dollars. So this is the equation, but note that the y-intercept doesn't make sense. Just like the y-intercept didn't make sense for the thing that Excel gave us that we didn't show the process of finding, we just showed it on the screen. The y-intercept doesn't make sense because it's a massively negative number. So at year 0, there were negative $41 trillion in expenses? Absolutely not. That is a horrible prediction. The least it could have been would be 0. And again, it wouldn't even make sense to go further in time backwards past the 40s or 30s or 50s, whenever that New Deal started officially. So question 4, I'm going to have to erase this, unfortunately. So just kind of hold on to that equation. Hopefully you wrote it down. I'll read the question while you're finishing that. Where does your line look like it will hit the vertical axis on the graph? What year does this vertical axis correspond to? How does this relate to the value of b in your equation in number 3? So where does it look like the line will hit on the axis? It looks like it hits, well, exactly here, because this is the axis. However, it's not a true y-axis because it's not representing the year 0, it's representing the year 1975. Remember, a true y-axis is supposed to start at 0, which this does not do. However, many times in the real world, we draw up axes that are not a true y-axis because they don't start at 0. So where does it look like your line will hit the vertical axis? It looks like it hits maybe about, I don't know, 60,000, 75,000, something like that. It's about 3/4 of the way down. If I just undo circling that point. There we go. Apparently I'd done a lot more. You can see that it's maybe 3/4 of the way to 100,000. So I'd say that's about 75K, and again in millions, so that's really 75 billion. What year does this vertical axis correspond to? Again, while not a true y-axis, it represents the year 1975. I'm just skipping writing sentences. How does this relate to the value of b in your equation? Well, it doesn't. It's not b. It's not the y-intercept because the y-intercept is supposed to represent year 0, whereas this represents the year 1975. So what I'd like to do really quickly is show you what this line would actually look like. So if we have, and that's going to be a terrible way of doing it. So here is somewhere way over here is 1975 and somewhere about the year 2000. And this is about the points that we have right there. Then over here, this will be the year 0. And if you trace this line all the way back, then this point right here, that would be the negative 413.26602, which again doesn't make sense. This is where you should actually stop. You shouldn't look anywhere past that in terms of going into the past, because it doesn't make sense to talk about years before 1940-ish. It doesn't make sense to have answers that are negative in terms of Social Security expenses. Okay, so let's clear our screen. Again, I hope you wrote that equation down, because it's going to come up again. maybe not, at least we'll compare to it. Now fill in the years since column. So there was a column here that was blank above, and now what we're going to do is fill it in. And this column we want to be the years since 1975. This is going to go pretty quickly. It's pretty easy to do. In 1975, that's been 0 years since 1975. In 1980, that's been 5 years. 1985, it's been 10 years. 1990, it's been 15. 95, 20. 2000, 25. 2005 would be 30. 2010 would be 35. Then 2013 would be 40, right? No, wrong. See, a lot of people get stuck right there, and they go, oh, okay, I'm just adding 5 years over and over and over. What's happening? Pay attention. You get used to, oh, it's just going up 5, 5, 5, say 5, 5, 5, 5, 5, 5, 5, 5, 5. But no, this only went up 3 more, so that's 38. Then 2017, that's another 4, so that's 42. 2020 would be 45, and there's still no Social Security outlays there. So we can't use that as a true point. Now compute the equation of the line going through the point. Now instead of using the true years, we're using the years since. And I've addressed how this can make better models on a short-term scale. It would make much more sense to only look at years in the range of when Social Security even exists. Now, we're not starting at the beginning of Social Security in the 40s or 50s. We are starting a few years into it, but that's okay. I could choose to start at the year 1980. I could choose to start in the year 2000. That's not the big deal. The big deal is that I'm trimming this from looking at 2,000 years worth of data to only about 50 or 60 years worth of data. All right, so now what we're going to do is compute the equation of the line going through the points. So now these are the same y values. It's the same y values as before, but it's the x values that are new. Instead of using the actual years, we're using the years since. Now, we've already done this in the past. We saw that we got a same slope, so hopefully that's going to happen again. It's just the intercept ultimately ends up being different. Now, I do need to clear my screen so I can give myself just a little more space. But those years since should be pretty easy to fill back in if you need to. All right, that'll work. I like red. Okay, so our slope, m, is y2 minus y1, so that's the 9, 4, 4, 8, 7, 8 minus the 6, 4, 6, 5, 8, all over the x2 minus x1, which is 42 minus 0. And when you do your math here, the top subtraction is the same. The bottom, the numbers are different, but the subtraction is the same. So you end up getting the exact same slope value of 20957.6. It's the same. But when we plug in the slope in one of these points, the y-intercept will be different. Let's switch to blue for that. So for the y equals mx plus b, we'll plug in the y, the m, and the x in order to find the b. It doesn't matter which of these 2 points you use, pick whichever one you prefer. I have said that if I've got a 0 somewhere, I prefer that one, and it's going to make this go really smoothly. So I'm going to choose this point. So the y value is the 64 grand, the x value is the 0. So 6, 4, 6, 5, 8 equals the m value, which is 20,957.6 times 0 plus b. Anything times 0 is 0. So we get 64658 equals b, which is our y-intercept. So that says that the starting value is 64,658 at 0. But we're not saying year 0. We're talking about years since 1975. That's our 0 for this model, which makes complete sense because that is exactly what we have the number being. So ultimately, our equation is y equals 20957.6x plus 64658. This intercept makes much more sense because it's a positive value and it's in the range of values that we see. So for the 500th time I've probably said it, doing years since is a much better linear model than years. All right. How much further do we want to get in this? So it's the same slope, but a different y-intercept. Hold on to that equation. If you didn't write it down, you got about 5 seconds to write it down. Snap a picture real quickly, whatever you have to do. It's going away. 3, 2, 1. It's gone. This. Too far. Now consider the trend line, the best fit line from the very beginning. I can't read that, unfortunately. In the graph below, how does this line differ from the one you drew? So now consider the trend line, which is right here. Now remember the one we drew, let me just really quickly put it up in black. The one we drew was anchoring the first and the last, and this is gonna not look as good because I'm not gonna take that time. That was the one we drew. So you could say that our line is a little above, or you could say the best fit line, which is the blue one, is lower. And that's about all you can really tell. Some people might be able to do that accurately enough to assess the slope, but that's really all I'm going to say. Then they say use both your lines. Use both your line, the equation that we just came up with, the thing that was just erased, the very last thing we wrote before erasing, and the best fit line to predict Social Security outlays in 2020. So we're going to use this line of best fit, and we're going to plug the year 2020 into that, maybe not plugging 2020 into it, but whatever represents the year 2020. Then we're going to use what we called, will that look good? Okay, yes, it will. The anchored, which was y equals, I wrote my numbers down, 20957.6x plus the 64658. So we're going to plug in whatever represents the year 2020 into the line of best fit, which Excel found the equation for us and always will, as well as the anchored one, which we found. See, the anchored method is very much an archaic version of the line of best fit. Again, we just don't consider all the middle points because, I mean, you saw how long it took just to do 2 points. Imagine trying to do that with all of them, especially the extra statistic stuff that's involved. It's horrible. All right, so for the best fit, BF for best fit. Now the year 2020, that represents, what year are we plugging in? 2020 in comparison to 1975 is going to be 45 years later. That's the number we're plugging into these two equations, not 2020, we're plugging in 45. So it's y equals for the line of best fit. And see, this equation is not the exact same because this equation, as the very original one, the original one had like a negative 7 million or 70 million here because they were considering all years. This is switched to years since. So that makes it more comparable. All right, so 20,559 times 45 minus 16,869. All right, so that's not going to be, I got to go off of this. This is where things just get a little weird, which is why I didn't want to do it earlier. 20,559 times 45 plus, I'm sorry, minus 16,869. And we get 908,286. Why does that look wrong? 2,559 times 45. 869. 869. Okay, that's fine. I have a handwritten error, that's all. That's what was throwing me off. Oh, shoot. This is why I don't like that. I always get confused. So that number is 908286. Then for the other one, for the anchored, it's y equals 20957.6 times the 45 plus 64658, which when we calculate that, 20957.6 times 45 plus 64658. And we get 1,007,750. And then the ultimate question is for number 10. That was off circled, isn't it? There we go. Do you think the actual spending will be more or less than the estimates from number 9? In other words, which one do you think is a better predictor? Which is better out of these two? So we're talking about the year 2020, and we want to know, is it the 900,000 or the million? And again, just tack on 6 extra zeros after those. So that's 908 trillion, or I'm sorry, billion versus 1 trillion. Well, look at this. Look at this year right here. If you trace that all the way over with a straight line, that number's already over 900,000 in the year since, which is 42, which would be 2017. Now look at these points. They're always going up. So I would say in the year 2020, I would anticipate that this dot is going to be somewhere higher. Now it may be a little higher, maybe a lot higher, but it's probably going to be at least jumping as much as they have in the past. Now, if you jump just that far, you're already in the 1 million range. So I would actually say it makes more sense for it to be the 107. And in fact, if you look at the table, this point right here was 944,878. This number is lower than that. And Social Security expenses have never gone down, so why would you think all of a sudden they're going to start going down? So I would say that this is the weaker answer, and that the other one, the million, billion, trillion, would be the better answer. So do you think the actual spending will be more or less than the estimates than 9? I would say more. All right. So that is that. The guided activity on the further pages down up to like 219, I really love that activity, but we just don't have time to do it, unfortunately. Let me clear my screen, go off to annotate. I'll at least show you and just really, really quickly talk about it. This activity is all about, there's this classic statement that half of all marriages end in divorce. And it's actually a pretty weak statement ultimately. That statement comes from the fact that in a given year, in the recent years, that is to say, if you look at the number of divorces occurring that year versus the number of marriages occurring in that year, for every 1 divorce, there's about 2 marriages. So that's where people try and claim that half of all marriages end in divorce, because every year, the number of divorces versus the number of marriages is about 1 to 2. For every 1 divorce, there's about 2 marriages. And look in 2010, about the same. 2004, about the same. 2000, about the same. 1990, about the same. 1980, about the same. But if you go further back, 1970 and on, it becomes less true. 700,000 versus 2 million, it's not the same as just doubling. 400,000 versus 1.5 million, that's definitely not true. So at some point around the 70s and 80s, this pattern changed. And they have you look at these in all sorts of different rates and just try and say, well, which one is kind of the best? How would you actually prefer divorce rates be explained so they're a little more accurate? And I wouldn't compare them to a total population because not everyone in the population is married. Not everyone in the population wants to get married, ultimately. Some people like just staying single or just having a domestic partner, if you will, whatever. Um, which rates seem to support the idea that half of all marriages end in divorce? Well, if you look at this one, at this column, divorces per 100 marriages, this is the thing where you're comparing these two values to each other as a ratio. And that's where you get that 50% approximation for the past roughly 50 years or so. Before then, that wasn't really the case. There were a lot fewer divorces per marriage. So does this conclusion that roughly half of all marriages end in divorce logically follow? Absolutely not. Absolutely not. It's just in a year, there's twice as many marriages as divorces. In order for that statement to be true, everyone would have to be getting divorced within a year. And I'm going to say this as jokingly as I possibly can, so please don't take offense to this, but it usually takes a while for you to grow disdain for your spouse to ultimately want to separate from them. You know, a couple of years. Yes, some marriages do end in a divorce within a month or weeks or a couple of months, but it's usually a few years before people start showing their true nature or just changing maybe too much for the other person, whatever it might be. We're not trying to get into the philosophical side of it too much. Then they show this scatter plot. Like I said, I'm just really quickly addressing this because it's one of my favorite activities, but it's long to talk about. So this is the divorces per 1,000 marriages total in the population. And this is ranking divorces per 1,000 marriages. So it's a ratio of divorces to marriages. And that's just total, not per year, total. And you can see that it's not too massive here, 5 divorces per 1,000 people that got married total. But over time, it's growing, it's growing, it's growing, it's growing. And if you look at the dots, we can see that there's a spike from 1960 to 1970 to 1980. And then all of a sudden, something changes dramatically and they start going down. Now this dot, 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 that line of best fit is considering all of these points. But in this region right here, it's pretty good for the most part. I don't know about this one. That's a little further off than the rest. So this is okay, but in this region over here, it is completely terrible as a predictor because the line of best fit is going up, but these dots are showing a downward trend, in fact. The divorces are actually becoming fewer and fewer. So what's going on with this? What could explain the divorce rate starting to fall after 1980 and this model becoming garbage? Well, first of all, people started living longer. So looking at an annual basis becomes an even worse model. Second of all, the biggest and most important issue for us, not just for the model, but as a people in general, in the 1960s, we finally had what we call the No-Fault Divorce Act. So before some point in the 60s, I want to say later in the 60s, and California was the first state to enact this, I believe, you couldn't get a divorce from someone unless you proved that, I mean, you can probably imagine what was happening, why people were getting divorced. It was usually abuse. There were other reasons as well, but that was usually what happened. You had to go to court, show that there was abuse, and that's how you got out of a marriage. So if it was just, you don't like each other, tough cookies, you're staying married. So California passed this. Other states started passing it, I mean, almost instantaneously, and then it was done for our whole country in the mid-70s, I want to say. So that is why you see this explosion of divorces, because you had all these people in the 40s, 50s, and 60s that had gotten married, wanted a divorce, but legally were not allowed to divorce because there was no fault. It was just they didn't like each other. But then the floodgates opened up and the divorce rate just skyrocketed for a bit. And by skyrocketed, I mean it just like multiplied by about 5. But once you open the floodgates and you got all these people that had been married for 10, 20, 30, 40 years, they got their divorces that they wanted finally. Well, now they start dropping off again because everyone's allowed to get a divorce. So you can be 1 year in, divorce, 5 years in, divorce. So this was kind of a correcting factor, and now they've gone down some. Now, is this likely to continue to trend this steeply? I doubt it. I think that it is still going to continue downward, but not in as steep of a manner. And also, the trend could completely change because in the past decade across the country, we've legalized marriage for everyone, not just opposite sex couples. So that could have an effect on the divorce rates. Would it have a drastic effect? I would say not too drastic because, just throwing a number out there, about 10% would be in this new classification, and 10% isn't exactly going to rock the boat as drastically. Oh, sorry for just making a bunch of noise, as this section right here. So this is a really wonderful example of how a mathematical model, when you look at it over too wide of a period, just falls apart because of some social dynamic. Also, we have a lot less people getting married now because it's a lot more socially acceptable to just live in a home together. In the 30s, 40s, 50s, your mom and dad were they're gonna beat you with a broomstick or something, right? I'm sorry for that joke. But nowadays it's, hey, I'm gonna do this. It's fine. Look at how many people do it. It's socially acceptable. All right.
And on that silly note, we will be calling it a day. I just want to mention one more time that the 5.4, I know we said we don't really do a lot of statistics in this class, and I know that the title of the section in the guided activities says Spotlight on Statistics, but again, we didn't really do any actual statistics with it, and the textbook section is not called statistics. So just making sure you understand that 5.4 homework is still part of your responsibilities. So 5.3 and 4 we finished today, so they're due in a week, along with everything else we had finished previously, plus the newest Excel assignment 5.1 lines due in a week, the newest video quiz due in a week, and then the midterm, the 12th and the 13th. Make sure that you do not forget those. Again, no excuses for missing the midterm. Remember, everything will be due by 11:59 p.m. the night of the 13th, just like any other assignment. You have your review in Canvas. You are allowed your calculators. Make sure you're prepared. Make sure you study lots and lots and lots. But besides that, have a good weekend. Email me if you have any questions. And per usual, take care, everybody.